So it's an honor to have Tom Deitrich with us today. I think I remember the first moment I think I ran into Tom. I was passing a seminar room and looked in and then walked in at Stanford and Margaret Jacks Hall. And there was some sort of very interesting debate going on some machine learning topic. I think a bunch of folks were there. And so it's just a memory that I've had of the past. I just remember the first glimmer of the energy of Tom Deitrich. And I've come to know and love his work over the years. Tom mentioned during our fireside chat, the video we did last night together, that we were talking a little bit about interests and this idea of that. I think we share one thing. We both have what we called it research attention deficit disorder. We get very curious and excited about many topics, and it's amazing to me how deep Tom goes on each of them that he attacks over the years. Tom did his undergraduate work at Oberlin, and then did his master's at UIUC. I think you mentioned you were following at the time the line of where you could find the best computer, sticking phones into these 300 baud sockets and so on in those days, and then did his graduate work at Stanford University, following, I guess, he ran into Bruce Buchanan after hanging out with Mikulski at UIUC, which got him into the machine learning world, and has worked on many different areas. I think following all the recent trends and leading some of them. I remember you and I were at the first UAI conference in 1985 together, and I remember you wearing a pair of shorts and asking hard questions in front of the room. Back in those days, I don't forget anything, Tom. So about these interesting interactions we've had over the years. Going to the probabilistic graphical models phase, I've always been touching on applications. Has done quite a lot of work during the Kalo project on desktop events and trying to infer the intentions of and goals of users from desktop streams of evidence. More recently has been looking like several of us here at the challenge of AI in the open world, issues about robustness and understandability of these algorithms. He was a leader in this whole area that's now called computational sustainability, working with Carla Gomes at Cornell at defining this area and somehow convincing the National Science Foundation to fund it deeply, looking at applications of optimization and other areas of machine intelligence to hard challenges with environment and speciation and resource management of planetary resources, sort of resonating with our AI for Earth effort here now at Microsoft. Today he'll be talking about a piece of this interesting area on robustness. I think it's an important aspect: anomaly detection, algorithms, explanations, and applications. So, Tom, thanks very much for being with us.
Thank you. Is this working yet? Yes. Oh. Now, can you hear me? Yes. Okay. So, of course, everything that I'm talking about today was done by someone else. So this is a collaboration with two of my fellow faculty in computer science, Alan Fern and Wenqin Wang. Wenqin is currently rotating at NSF as a program manager, but he'll be back in the fall. And then two faculty from statistics, Sharmadeep Bhattacharya and Debashis Mondal. And at least one of them did their thesis at UW, but I don't remember which one. And then several graduate students, and as their contributions come up, I'll be pointing those out in the talk. So I have a sort of long agenda here. This is more than I would usually try to cover in one talk, but some of them are fairly straightforward. So what I want to do is start by defining this question of anomaly detection. What do we mean by that? Because that's not a terribly well-defined term. And then I'll briefly review a big benchmarking effort we did. Mostly in the knowledge discovery and database community, there have been many algorithms published in the anomaly detection area I think largely because they have many business problems in fraud detection and management, and this is a big tool there. And but a lot of those are just publishing an algorithm, a mechanism, without any kind of a theoretical foundation. And so we wanted to understand them, and then we've done a bit of work on a probably approximately correct type of machine learning theory for what we call rare pattern anomaly detection. Then I'll talk about scenarios like fraud detection, where you have a ranked list of anomalous transactions or users or whatever, and now you have an analyst in the loop, and so you want to show the analyst, say your number one candidate, and explain to them why you think it's anomalous. Obviously, it's not sufficient to dump a 180 element vector on them and say, we think this is an anomalous user, but we want, so I'll talk about some very simple feature-based explanations. And then if we've got the analyst in the loop, we can also get feedback from them and use that to re-rank our candidates as we're presenting them. And that turns out, at least in our benchmarking, to be really powerful. And then I'll wrap up with two applications. One, which is a big sort of sustainability application involving deploying 20,000 weather stations in sub-Saharan Africa, and then trying to automatically detect when stations break and sensors break and so on. And the other is a sort of open world AI problem, which is the problem of open category classification in say, multi-class classification. So, defining anomalies. So we're going to assume that our data are just feature vectors in d-dimensional real space, and that we have a data set that is a mixture of what we'll call the nominal points, so that we don't call them the normal points, and the others we'll call the anomalies. And our assumption is that the anomalies are generated by a different generative process than the nominal points. But typically our data will be unlabeled. We'll talk about that, I guess, on the next slide, which is there are really three settings. So in some cases, people have tried to formulate this as a supervised learning problem, so we get some labeled data. But in most of the sort of anomaly detection applications, the anomalies are quite rare. Fortunately, 50% of our users are not trying to defraud us. Although maybe it seems like that at times. And so we would have severe class imbalance if we approach things from that perspective. Another possibility is that we are training on clean data that has no anomalies in it, but then maybe at test time we're going to get contaminated data, and we need to identify those contaminants. And that's what happens in the open category case. And then another situation is where our training data is contaminated with some kinds of anomalies, and we want to figure out which points those might be. So we'll be looking at those. So I think a very important consideration here is this assumption I call the WDAD assumption, the assumption that the anomalies are drawn from a well-defined probability distribution. So just to back up, if you're formulating things in a supervised learning way, you are essentially assuming my anomalies are coming from some well-defined distribution, right? And I can learn about that. But if we're in an adversarial setting, like in the fraud or cybersecurity kinds of settings, then that really is not a valid assumption to make, right? In fact, our adversaries are constantly trying to defeat whatever distributional assumptions we've made. Another case, in the weather network case, it seems like it's adversarial in the sense that it's sort of the number of ways something can be anomalous is a sort of an unbounded set. And I guess technically speaking, it's still a well-defined probability distribution, but you don't have nearly enough data to have sampled the whole thing. So you really can't model it. And another case that's come up, I've collaborated a little bit with Kiri Wagstaff at the Jet Propulsion Laboratory. And there, the user is usually a scientist, and they're looking at data coming from some sensor. Like she's worked on some spectrometers that are on the Mars Science Observatory. And what the expert wants is to find the interesting data points. And now the first few interesting data points are actually, ways that the instrument fails, and they need to understand those. But then they start being interested in, unusual spectra that might signal some interest in compounds. But then once they've seen those, then they say, well, don't show me any more of those. I want to see, show me real anomalies. And so it's a time-changing notion. So I think, we need to be sensitive to when it's appropriate to make this assumption. So there are, I think, two main strategies, I think, for unsupervised anomaly detection, and it depends a lot on this parameter that we call alpha, which is the fraction of the training points or test points that will be these anomalies. If alpha is reasonably large, then we can think about fitting something like a two-component mixture model and actually trying to model that anomaly distribution if we're willing to make this well-defined distribution assumption. There are various conditions for that to work. Alternatively, if the proportion of anomalies is very small, as it typically is in these fraud cases, then the main strategy is to treat it as a problem of outlier detection. So we're going to try to model the distribution of the nominal points, the ordinary users, and then treat the outliers as our candidate anomalies. And the advantage there is that we don't have to make any assumption about the distribution. But of course, if the anomalies are not outliers, then we will miss some of them. And also, if the nominal distribution itself has very heavy tails, so that it just naturally has a lot of outliers, this won't work either. So as I mentioned, in the KDD literature, there must be 20 or 30 different algorithms that have been published. There's a huge number of papers there, and a problem with many of these is that they unlike in a lot of other parts of machine learning and computer vision and natural language processing, there's not a large collection of standard benchmark data sets that you could do a thorough evaluation on these algorithms. Often, there's some sort of a corporate application with a proprietary data set that they can't share. And then the most popular benchmark data set is this computer intrusion data set that was collected as part of a DARPA project back in the late 90s. And it turns out to be extremely easy. So we strongly believe in benchmarking and the need to have a large and constantly growing collection of anomaly benchmarks. And so my student Andrew Emmett conducted a big benchmarking study. And our methodology was to repurpose existing supervised learning benchmarks, either classification or regression problems. So we chose 19 data sets from the UC Irvine repository, which were all the data sets that satisfied a set of criteria we had. We wanted real valued features, we wanted enough data, we wanted enough dimension. And then we would choose one or more of the classes to be these anomaly classes, the source of our anomalies, and the rest to be the nominals. And this ensures that our anomaly points are being created by some process that's different from the data that's creating the nominals. And then we systematically varied things like alpha, the relative frequency of the anomalies, the difficulty of the points, like how deeply embedded are they inside our nominal distribution versus how much are they outliers. We added redundant or irrelevant features to see how much that could defeat the algorithms. And we also looked at how clustered the anomaly points are, right? Because to a large extent, these anomaly detection algorithms are all something that's some form of approximate density estimation, right? You're essentially trying to model the probability density of the nominal points and then score points according to how the very low density points are your anomalies. Now, if the anomalies are all tightly clustered, then they form a little peak of density. They don't look like they're low density anymore, and so you'll miss them. So we were interested in that. And we created 20 replicates for each configuration of these manipulated values, and that gave us about 25,000 different benchmark data sets. So then we compared a set of 8 different algorithms. I won't go through all of them, but basically there are some that are doing density estimation, some that are we call the quantile-based methods, like the one-class support vector machine is probably the best known of those. It tries to find a boundary around your data that contains, say, 1 minus delta of your data for some quantile you choose, delta. There are nearest neighbor type distance methods, and then there are these projection methods. And I want to talk about these because these two algorithms turn out to be very attractive for many reasons. So the first algorithm, and the one that actually performed the best on our benchmarking exercise, is something called the isolation forest. Those of you who know me know I love decision trees and anything, random forests, boosting, all these things. So I had a natural affinity for this algorithm, although when I first saw this paper came out, I said, this is such a weird idea. But the basic idea is we're going to construct a completely random binary tree, right? Again, recall that our data are not labeled. So we just choose one of the attributes at random, and then we choose a splitting threshold uniformly at random out of the observed range of the data. And then we do that, split the data recursively, and we split this in some sense overfitting radically until every data point is in its own leaf in the tree. I mean, in the paper, actually, they have ways of avoiding having to do that. You can stop the splitting at some point. And the idea, and we'll build an ensemble of these, and the statistic we're interested in is actually the depth of a point in the tree, the depth at which a point becomes completely isolated. Like, let's say that my one data point xi is the only data point in this leaf node here. Then we would say xi is isolated at depth 3. And the intuition here is, in some sense, we're just throwing like a dartboard random separators at the data, and how many random separations do we have to do before a data point is separated from all the rest of the data? And the intuition is, well, if you're an outlier, it's going to take only a few random shots and we'll get you isolated. Whereas if you're deeply embedded in a tight cluster, I'm going to have to split forever to get down to isolating you. And so the anomaly score that we get, so D bar is going to be the average isolation depth over the 100 trees, say, some ensemble. And then one nice thing in this paper is that they calculate the expected isolation depth from a little bit of theory, and so then they can normalize this so that it lies in a 0-1 scale where anomalies are given scores close to 1, and the nominal points typically have scores less than 0.5 or around 0.5. The other algorithm I wanted to talk about, yes? Mm-hmm.
Favor a particular basis of the features, right? If you have a linear transform of the features, you get a different basis. This
right.
is not a basis invariant. So, like, for example, if you have, like, the point is not obviously outlier in one basis,
right.
But like if you transform it, for example, if you're like a sphere and then like it's fuzzy around that, like I don't know if you can tell just by looking at this via one basis.
It's true, and so of course we've also looked at randomly rotating the data before we top it up. It helps a little bit, but the randomness increases the variance of the isolation depth, so then we have to make the ensemble bigger. So it hasn't been enough of a gain to be worthwhile to us because the memory starts to be an issue here. So
does this problem arise frequently enough in nature or like in practice that you should actually care about this?
Well, so in nature, I don't know. In our benchmark data sets and in like our fraud detection applications, the features are generally meaningful. So, and we're not doing this on images or things like this where pixel 25 has no particular meaning at all, right? So I certainly wouldn't use this out of the box on images. That would be crazy. Maybe I would use it in the penultimate layer of a CNN or something. Not even convinced that would be a good idea, but
maybe some like relationship between variables, like say x
certainly
squared
if
plus y plus z squared is like the meaningful variable and like the outlier.
But usually, I mean, just as decision trees basically are looking at higher order interactions, right? As you go deeper, you're looking at these things pretty much follow the data distribution, right? We only put splits where we have data. So they do a pretty good job. There was an interesting paper by Nina Mishra, I think, and colleagues at ICML a couple of years ago, where they analyzed a slight variant of this algorithm and showed that the isolation depth is related to an LP norm on the distance between the outlier and the data. So in this case, basically an L1 norm. You can sort of imagine how this would be sort of like an L1 distance. So it has I mean, I think, you know, if you look at these different these different algorithms, I think a lot of them are essentially doing something that's very similar. I mean, the nearest neighbor algorithms are calculating some distance, and the isolation forest is definitely calculating something like a distance also. And clearly, these things are using a kernel distance, and these things are using something like a Gaussian kernel in the original space. So, yeah, I mean, of course, you could apply PCA to try to, you know, rectify the data in some sense. The other method that I want to mention, I should say, are there any other questions? Sorry. Yes?
Do any of your data sets, benchmark data sets, include behavioral data, so sequential data that was generated by capturing traces of someone's behavior, like network intruders' behavior?
No. I mean, so when we applied this in this DARPA, we were in this DARPA program called ADAMS. And there we were looking at an organization that had 5,000 employees, and we had actual sort of desktop spyware installed, monitoring software on their desktops. They were working for some organization in the military-industrial complex. That's all I'm allowed to say. But so we could go down and really look at like every email message they sent and even the content and all that stuff. But we summarized that at a daily time step and turned it into sort of a vector of how many emails did they send, how many websites did they visit, how many this and that and the other thing. And then we also did some normalization to try to deal with both asking how unusual was this day compared to the typical day of this user, and how unusual was this user on this day compared to everybody else in the company on that day. Because otherwise we had these things where some new web link would be sent out through the whole company and everybody would go visit it, and nobody had ever visited that link before, and we would get all excited if we were only looking at one user. So, I mean, so we had to do some pretty serious feature engineering to turn this into something that was, you know, almost IID. But then all these algorithms are purely for that sort of feature vector case, and in my weather data, we're again having to figure out how we can engineer the features to take what is very much a spatial temporal time series and turn it into little database views that are approximately exchangeable. So. Okay, well, the second algorithm I want to mention, it's even simpler, is called LODA. Given a set of data points, what it does is create a set of capital M, say 100, sparse random projections. So it randomly chooses square root of D, where D is the dimension of the data, square root of D of the dimensions, and then defines a random projection onto a one dimension, and then fits a one-dimensional density model. I've drawn it as a kernel density estimate, but they actually use an adaptive histogram estimator. And then what they do is just calculate the average of the minus log density of a query point, so the average surprise. And we can see if we took a data point like this one right here, it would have a pretty high probability in this projection. But of course, if we got some other projection, then it would be mapped to a low density tail. And so this is an extremely simple idea, but also works surprisingly well, presumably because there are not super high order interactions in our data. So like looking at 3 or 4 dimensions at a time works pretty well. So then, how do we do our analysis? I point you to the archive papers for the details, but we basically chose a couple of metrics, either the area under the ROC curve, which we put through a logit transform, or the log of the lift, which is related to the area under the precision recall curve, and just tried to set up a linear model to say across all of these benchmarks, how could we explain, how much of the variation in the metric could be explained by the relative frequency of the anomalies, the difficulty of the points, the clusteredness, the amount of irrelevant features, what we call the mother set, the original, the domain from which the original data set was drawn, and which algorithm we were using. Because I wanted to say, well, a typical finding in machine learning is that the choice of problem is much more important than which algorithm you use, and we were curious if that was true here or not. And the answer is pretty much true also. So here are those sort of 5 factors, and here is the change in the R squared, basically how much variation can we explain in these 2 metrics. So under the area under the ROC curve, if we take a model and delete the data set feature, how much R squared do we lose, or how much can we assign to the data set? And that's the most important variable for explaining the observed AUC. Next is the relative frequency. So if you have a data set where the anomalies are very rare, we can do very well, right? Because we have very little contamination. As the anomalies get more common, then these techniques fail. Because really only one of them has any explicit attempt to be robust and use a robust loss. That's this technique called robust kernel density estimation. All the others are just plunging forward, fitting some kind of a model. And so the choice of algorithm is really only the 3rd most important factor, and really not a whole lot more important than the others. But with that caveat, here are the different algorithms that we tested, sorted by decreasing change in the metric compared to a control baseline. And what we see is that actually the isolation forest was performing better than the other methods. And then there's sort of like a 5-way tie for second place. And surprisingly, the one-class support vector machine and support vector data description really performed the worst on these problems, which was quite a shock, because I think if you asked a random machine learning person, if I had a one-class problem and I needed to fit it, what would you use? And they'd all say, well, gee, how about, Bernard Scholkopf has this algorithm, right? We're a little puzzled about this, and of course it's possible that we just didn't tune these properly, although we tried a lot of things, but we wanted to have a fully automated tuning procedure, and so it may be that we didn't do that well. But there have been some papers recently in the literature on auto-tuning those, and so we were trying to use the current best practices. My own hypothesis here is that the metrics that we're evaluating on are really related to how well you can rank the data points, whereas these methods really just set it up as are you inside or outside of a particular quantile, a particular level set of the density. So it's not clear that they're really being trained for the right to do well on these metrics. And so maybe that's why they don't do as well as some of these more distancy-based or density-based approaches. So we also find in general that the isolation forest is a bit more robust to irrelevant features, and that it's also a bit more robust to clustered anomaly points. So that may be why it has this slight advantage over the other methods. Okay, well, let's move on now to thinking about whether we could have some kind of a theory to explain what's going on. Because one of the things we were quite surprised at is when we look at the learning curves, these algorithms all learn quite quickly. And of course, if we look at, well, what existing sample complexity theory do we have for this kind of one class or density estimation, it's often quite discouraging, right? So if you look at full density estimation, you typically need a number of examples that's exponential in the dimension of the data. That doesn't match our experience. And for the quantile methods, there are polynomial sample complexity results. Our observations are maybe more consistent with something polynomial time. So my colleague Alan Fern came up with this theory we call rare pattern anomaly detection, and it works as follows. So we imagine we're going to define, this is very, Valiant style pack learning kind of thing. We're going to define a space of patterns or regions. So we'll define a pattern as a Boolean function that takes a point in d-dimensional space and maps it to either 0 or 1. So it might be a half plane or an axis parallel hyperrectangle, some kind of region. and we'll let capital H be the set of all the patterns in our pattern space. And then the idea is to define a notion of a rare pattern and a common pattern. And to do this, we need to do a little bit of being careful about measures. So we're going to assume some baseline measure. So if we're in, say, a hyperbox in d-dimensional space, we might use just the Lebesgue measure, the uniform measure over that. But if we're in unbounded real space, we need to use something like a standard multivariate Gaussian as our baseline measure. And we'll let mu of h be the measure of that pattern, pattern h. And then let's let p be the probability density of the nominal data points. And it's defined over RD also. And we'll let p of h be the probability assigned to pattern h. And so we'll say a pattern h is tau rare if the sort of normalized probability density is less than or equal to some threshold tau. And otherwise, we'll say that pattern is tau common. And then our definition of what we want is we're going to say a data point now, a query point, is tau rare if there exists a tau rare pattern that data point belongs to, right? So that data point belongs in pattern H, and H is tau rare. So that means there's some way of looking at the data. There's some bin in the data that this query point X belongs to that is very unusual under the nominal distribution. And so then our goal, an ideal anomaly detection algorithm would output all of the tau rare query points in a test set and not output any of the tau common points. That would be the idea. So I guess what's say interesting about this model is that instead of trying to estimate the entire density, or even trying to estimate a level set of the density, we're just choosing some set of regions in the space and just trying to figure out what their roughly what their probability density is, or the probability of those. So, and I think that this is why if we don't have too many of those regions, then we can get uniformly good estimates over most of them from a relatively small sample. So we define an algorithm to be probably approximately correct RPAD if for any probability density p and any threshold tau, it draws a polynomial sized sample, and then with probability 1 minus epsilon, it detects all the tau rare points and rejects, does not output any tau plus epsilon common points. So we have to introduce this sort of elbow room parameter to allow the algorithm to make some mistakes. So it's allowed, if a point is between tau plus epsilon rare and tau rare, then the algorithm can do anything it wants there. And so what we end up with is an algorithm such as the following. If we can draw a polynomial sized sample, and we'll talk about this, what this is in a moment, and then we just estimate p hat is the fraction of the sample that belongs to each of our patterns. And then we can calculate the normalized rareness, and then we just say a query point is declared to be an anomaly if one of these tau rare patterns is made true by that query point. So we can prove a sample complexity result that says that the number of samples we need is on the order of 1 over epsilon squared, the log of the number of patterns, plus log of 1 over delta. So very kind of typical PAC result. It's a little unfortunate that this is epsilon squared here. So that's going to mean, if we want epsilon to be 0.01, then we're going to, need what, 10,000. This will be a big number, a big constant. And then we can get a VC dimension version of this, where the VC dimension plugs in here times log of 1 over epsilon squared. So there are lots of different, practical algorithms you can design with this procedure. Half spaces and axis-aligned hyperrectangles. And in our paper, we worked out the VC dimension of all of these. And in particular, we designed a version of the isolation forest that exactly matches this theory. And to do that, we, the pattern space has to be chosen a priori in this theory. It can't be adaptive to the data. So to deal with that, we use the usual trick of, say, taking our training data and dividing it in half, and using half the data to grow an isolation tree to some fixed depth k. And then using the second half of the data, that fixes our pattern space. And then the second half of the data, we can estimate the probability of all of these bins. And so here are some examples on some data sets where the plot on the left is for the isolation forest, the actual isolation forest algorithm, grown to a fixed depth k. And this is our theoretical version of it, also at depth k. The vertical axis is the area under the ROC curve, and I apologize that the axes are different in the two plots. And then these different lines are for different depths of tree. But if we just look, in this case, the depth 1 trees actually worked the best. And we see that, that in this case, the pattern min method actually does a little bit better than the isolation forest on the area under the ROC curve. For another data set, particle, the isolation forest does much better, because notice this is 0.71 down to 6.6, and this would be 6.6 down to 5.2. So all of these curves basically are below all of these. So the isolation forest was much better. And then here's the data set shuttle, where the RPAD, the theoretically inspired algorithm, is actually doing quite a bit better than isolation forest. And this time I did get the axes aligned. So, so I think qualitatively, well, the shapes of the curves aren't always the same. Yeah, there's sometimes some funny business going on with very small samples, right? This is particularly weird that we do very well with very small samples. And there's an interesting phenomenon going on here that we don't fully understand. But when you have a training sample and it includes some amount of contamination, if you a standard practice that's done in the isolation forest is to train on actually subsets of the data, not on the entire data set. And the idea is that you're kind of thinning out. It's a robustification strategy. By training on smaller subsamples, you have the absolute number of contaminating points is reduced. The fraction isn't reduced, but it seems that that if you have like a tight cluster of points, you're reducing that local density of that cluster. And I think this helps the algorithms do a better job. But we don't have a good theoretical understanding of this. But empirically, even the original authors of the isolation forest algorithm say that you should train on a small subsets of the data rather than the entire data set, and that this often helps. And for those of us in machine learning, it's like, what? You're not using all your data? But of course, we're building an ensemble. So across the whole ensemble, we're using all of our data. And the smaller the subsets, the bigger the ensemble needs to be, because you also have to reduce the variance that you've introduced by choosing these random subsets. So, so this is a paradox that this kind of thing where the small samples actually are performing well. I mean, it's not observed all the time, but it's observed enough of the time that we think it's a real phenomenon, and we're trying to find a nice theoretical understanding of it. Okay, so the conclusions from this is that we feel that this rare pattern anomaly detection theory captures a lot of the behavior of the isolation forest or of LODA, because these methods are solving a simpler problem than full density estimation or even estimating level sets of the density. So I guess maybe I should pause and say, are there any questions about that? Yes.
How does this algorithm compare on a high-dimensional data, very high-dimensional data?
Well, I would guess that on very high-dimensional data, you need to use a very large ensemble of trees, right? You would need, let's see, what's the right way to talk about this? I mean, if your space of rare patterns is in some sense, I think you want to, if you have a distribution of the data, you want to have these rare patterns kind of surrounding the data, right? And obviously one intuition is that in high dimensional space, you're going to need a lot of those patterns surrounding the cloud of data. And so the number of patterns you might need to really tile the entire region might grow exponentially. And so our result says, well, the sample size is polynomial in the number of patterns, but the number of patterns that you need might be exponential. So that's a good question.
Have you tried this as
We have not tried this on a bag of words thing, for example, Now, one might hope, I'll do the standard machine learning thing and say, oh, but the data really lives in a low-dimensional manifold. And so all we have to do is identify that manifold. And but we know that tree-type algorithms will, in some sense, follow that manifold. And so we'll still do okay. I'm waving my hands. Yeah. Yes?
So it seems like this theory requires knowing the pattern space, right? But then if you're dealing with anomaly detection, I mean, many say, successful intrusions happen exactly because there is some sort of behavioral pattern that you didn't take into account. And so the adversary was able to exploit it. So is there a way to extend or fix this theory to maybe at least give you some indication that there is something in the data for which you don't maybe have a pattern, or you didn't list a pattern, but that it may be an anomaly?
Well, if we think about what, for instance, the isolation forest does, it actually partitions the entire input space into patterns. So there is always a pattern for every possible observation. Many of those patterns will be essentially empty. In fact, I sort of skipped over a little detail of the isolation forest, but when you do a split at a node and you split the data, there you now have, you keep track of, there's little empty spaces between the observed range of the data in the children and the observed range in the parent. And they're actually, a query point can fall into that empty space in between the observed ranges. I'm being very inarticulate here about this, but if I have a set of data points along a line and I choose an arbitrary split, right? There's going to be some space between adjacent instances, and that empty space, effectively, the algorithm allocates two additional patterns for that empty space. Because if a query point comes down, it's considered to be isolated if it falls into the space. It was inside the range of the parent and outside the range of the child. And that turns out to be really important. If you don't do this right, then the performance of the algorithm suffers quite a lot. So I guess my first point would be that if we use some of the data to build the tree structure, and if the tree structure is really following the structure of the data, then we will have tiled the space nicely. And every leaf node, by construction, is going to be rare because it will have at most one point in it.
Yeah.
So we're going to have a lot of regions that have essentially 0 points or 1 point in them, and we've also completely tiled the space. So if there is an unusual behavior, it will fall into one of these empty spaces, basically, and will be detected.
Then how do you tell between interesting anomalous behaviors and uninteresting anomalous behaviors?
Well,
because
we're only doing outlier detection here, and we have no knowledge of that an outlier. We can't tell the difference between an outlier that's part of the natural variation of the distribution and an outlier that's due to some unusual behavior that's caused by something different, like a fraudster or something. Yeah. In fact, of course, a fraudster is going to try to mimic the nominal distribution, and so we might want to try to use some essential behavior things that the fraudulent user is not able to manipulate to help us detect their behavior, right? But all I'll say is that in the competitions inside this DARPA program, we were number one in several months using these kind of techniques. So maybe that's a tribute to our feature engineering skills, or maybe the red team made it too easy. I don't know, but these methods were working pretty well. And we're competing against an IBM team that actually has a product in this space, so I don't know. Anything else? Okay. Well, let me move on now to assuming that we can find these anomalies, how can we explain them to the user? So our basic idea is the following. We were really troubled by what constitutes a good explanation and how could we measure that in a rigorous way without doing human subject studies. And so here is the thing that we came up with. We imagined that the goal of our anomaly detection system is to persuade the analyst that a candidate anomaly is a real anomaly. And the idea is we're going to expose one feature at a time to the analyst. in the worst case, until we've presented all of the different features to the analyst. And then with an appropriate visualization tool, until we've either convinced the analyst that it really is an anomaly or the analyst says, no, it isn't. And we sort of view the analyst, their job is really to decide whether to, say, launch an internal investigation, like a fraud investigation, or not. So this is the kind of model here. And so we call this a sequential feature explanation. And we had a paper at UAI 2 years ago on this. And so we do so in pictures, right? The vertical axis here is the experts or the analyst's assessment of the probability that the data point is a nominal, not an anomaly, given the features you've seen so far. So we'll say that notionally it starts out pretty close to 1 because, say, 1 minus epsilon, where epsilon is the background probability of being an anomaly. And our sequential feature explanation is some permutation of the features. Say feature number 3 we think is the most important. So we start presenting these features to the expert, and if we're being persuasive, the expert's posterior belief that this is a normal point starts to drop, and hopefully goes to 0. And what we do is choose some threshold, and we say that we talk about our metric is something we call the minimum feature prefix, MFP, which is in this case would be 4. It took us, the first 4 features in our ordering were required to drive the expert's assessment down below, say, whatever that is, 0.25. So this is the MFP is our metric, and across a whole data set of anomalies, we'll look at the average of that as being our performance metric. So if our anomaly detector is working well, then, or if we have a good explanation algorithm, it should use short explanations. So this is, it's sort of the minimum kind of thing we might have, and obviously it's only appropriate for problems where the features are meaningful. So in this case, our technique, we relied on another one of our anomaly detectors, which is an ensemble of Gaussian mixture models, so the EGMM algorithm. And we had originally developed this just as a control. So we apply PCA, and then in the PCA space, we fit an ensemble of Gaussian mixture models where we randomly vary the number of mixture components and the starting initialization, and we discard mixture components that didn't fit the data very well, and of the ones that survive, then we calculate we can get our anomaly score is actually the average surprise across those models. So it's the product of the density estimates, I guess. And so then we use a simple greedy algorithm. So the score of a particular feature is how much the log likelihood drops when we marginalize out, or I've got this backwards, there should probably be a minus sign here. It's how much the surprise decreases when we compare the marginalized distribution to the original distribution. So this will always have a higher probability density after we've marginalized out one feature than the full distribution had. And so we do this, we score each feature, and the one that led to the biggest change in the density, we say that's the feature with the biggest impact, and then we remove it from this set of candidate features and add it to our answer, and just do that in a greedy fashion. And again, we used a bunch of our data sets. We only used 7 of the domains, the UCI domains, instead of 19 in this study. And instead of using real human analysts, we trained regularized random forests on the supervised version of the data, so they could see all of the data. And then we used, and the question was, we would convince them if they saw all the first 4 features, is their predicted probability that it belongs to the anomaly class or to the nominal class as it dropped below some threshold. And so we compared against a random ordering of the features and against an oracle that actually knows the labels of the data, right? And what we saw was that we always did better than random. So and sometimes we do almost as well as the oracle. So this is random ordering. This is the oracle in blue, and this is our greedy algorithm. Sometimes we don't do as well. I guess one thing that's kind of interesting is that for most of these Irvine type domains, on average, the oracle only needs to show the analyst one or at most two features to give an explanation. So that's convincing. So that's kind of interesting. And this gives us a kind of metric of how hard a data set is. So if we look at the KD 1999 data set, for instance, it's always the case that you need only one feature. Even our algorithm only needs to use one feature to explain an anomaly. Whereas if we look at this Adams insider threat database, you need about 7 on average. So it's a much more challenging problem. Well, if we're going to be talking to an analyst and getting and convincing them, we can also get feedback from an analyst. So we wanted to also then look at, could we take the feedback from the analyst and feed it back into our anomaly detection process to re-rank the candidates that we have. And so we had a paper at ICDM a year and a half ago showing that this could be a potentially big win. So what we do is we require one parameter, which is a quantile. It basically corresponds to how many cases can an analyst look at in a given, like in a day or a month, whatever the time period is that we're analyzing. And so the idea is that the analyst can look at, say, 60 cases in a month. We want to optimize the 60 cases we present. So we start by presenting to the analyst the highest scoring anomaly we have, and then the analyst says, yes, that's a case, and I'm going to open investigation, or no, it isn't. And then we feedback that. And what we try to do is to learn to reweight. In this case, we're working with the LODA anomaly detector, which, remember, creates a bunch of random projections, one-dimensional random projections. So we learn to reweight those projections to try to rank all of the known anomalies above quantile tau and all of the known nominals below quantile tau. And to do this, we used a modification of a method from Stephen Boyd and famous colleagues called accuracy at the top that was published at NIPS several years ago now. And so we're re-ranking based on feedback from the expert, and we call this active anomaly detection. Actually, I don't think I guess the only interesting thing is that, if the anomalies are fairly rare, then we will have a significant false alarm rate. So it could very well be that the first 3 or 4 or 5, 10 cases we show to the analyst none of them are actual fraud cases. What can we do? Well, one of the advantages of this, of having this threshold tau, is that even with no positive examples, we still learn to push down all of those non-anomalies below this threshold tau. And so this seems to help us learn even without any positives. But we had to make some minor modifications. So we compared against a baseline where we do no learning. We just take our initial anomaly scores and present them in that order. We looked at randomly ordering them, and then this is our method. And then there are 2 other methods in the literature, one called AI2, which I don't think has ever been published except as a CSAIL tech report. And so it's probably a class project or something, although it works quite well in some cases. And then there's something called SSAD, which was in a JAIR paper. And their method from Gurnitz et al. is called marginalize and cluster, I think. We thought we had an idea for improving it using our accuracy at the top method, but as you'll see, it was not an improvement, but just for completeness. And so what we're going to plot in these plots is, along the horizontal axis, is how many cases have we presented to the analyst, and the vertical axis is how many of them turned out to be true anomalies. And again, all this is done with a simulated analyst and so on. But and so we can see that our baseline method is this blue curve. And so if we have a budget of 60 cases we can look at, we find about, 25 or 26 or something. Whereas if we can incorporate our feedback, we get 45. So huge advantage from having the analyst in the loop. However, this is the KD 1999 data set, which is extremely easy. So let's move on to some other ones. So this is the abalone data set. And here, well, early on, we get some benefit of our method over our baseline, right? This is our no feedback is the blue curve, and ours is the red curve. And then this is this SSAD method, which is doing just about as well as ours. But if we say, well, suppose we only had time to look at 20 cases, then we'd still be seeing, more than a factor of 2 improvement. Eventually, obviously, if you go out far enough on this, there will be no benefit, because eventually we'll have shown everything to the analyst. So here's another one for thyroid. In this case, again, compared to our baseline, we're doing pretty well. In this case, this AI2 method is doing almost as well as we are. But again, the benefit is potentially almost a factor of 2 in terms of the number of anomalies we can detect. And in the mammography, similar story. So in general, for all of these, we're seeing that incorporating the analyst feedback can be really powerful, at least for this LODA algorithm. But now let me speculate about why this might be overly optimistic. We have to remember that these data sets that we've constructed here are constructed from these supervised learning data sets. And what's going on when we reweight these different projections, we're essentially reweighting the original features and putting more weight on some than on others. And so it could be that because our anomalies are coming from classes in a classification problem that were presumably determined to be classes because they were believed to be separable using the features, right? It may be that we're essentially, in a sort of sneaky way, learning a classifier and taking advantage of that. So it's not clear, in a real fraud detection case, would we get these same sort of factor of 2 improvements. However, we have a paper under review right now at KDD where we're doing reweighting for isolation forest, using a sort of online learning strategy. And we have applied this to this advanced persistent threat cybersecurity case, which is not a supervised learning case, and we're still seeing a substantial, not a factor of 2, but a substantial benefit from integrating the feedback. Yes?
Would it help to put the label noise to answer that question?
Label,
so you have your classes.
Right.
If you put some label noise, it's going to start mixing the classes. They won't be separable anymore.
Oh, you mean when we constructed
Yeah.
that's interesting. We should, it's interesting. We should maybe look at that. That would be a good test, at least for this particularly. Yeah. Right, and I guess another thing is we could create benchmarks where our nominal points come from, say, just one class, and the anomalies are from the mixture of all the other classes. So we might think that, or maybe we should use lots of each classes so that there's probably not a simple decision boundary that separates the nominals from the anomalies, because there'll be very, very multimodal distributions on both sides. Yeah.
So the feedback you had here is very example driven, right? On the analyst judging things.
Right.
It seems like you could also order it to be feature driven, or going back to your pattern terminology, patterns, right? So like in fraud cases, people are often interested in the patterns, like, a small gas station purchase followed by a big purchase is a pattern, right?
Right.
And instead the anomalies are evidence that this pattern exists.
Right.
Have you thought about trying to order in other ways where people might be able to give a more sample efficient feedback over an entire feature as to whether or not I believe something anomalous is happening here?
We have not. We did try back in the, to do some sort of model-based work back in the insider threat data set, where we had some theories of insider threats, and we designed features specifically to look for those threats, like someone copying a large number of files onto a thumb drive, but this is, you have in mind maybe more of a knowledge discovery setting where the analyst looks at our anomalies and says, maybe can you do, like as we've been discussing today, maybe some cluster analysis of these anomalies the way you guys are clustering mistakes, and say, I see sort of a pattern in these, and this looks completely bogus to me. Looks like just some side effect of some instrument, so I don't want to see any more of these cases like this, for instance, or this looks interesting to me. Yeah, so everything that looks like this, let me label that whole cluster. Yeah.
How you select the examples, that you select them based on a set-based criterion, right? If you want
Right.
to exclude a whole feature, if you just randomly select examples, chances are you want to exclude that feature. Whereas if you start selecting them in conjunction, you can do that.
Yes. Yeah. We did look at whether the sort of select the biggest anomaly is the right thing to do. And Wayne Keen, you may or may not know, but when he was a graduate student, he was working on rare category discovery. And there you do have some diversity tricks. And so, and of course, yeah, so we could think of this as also, could we elicit from the expert, again, consistent with some of the things I've been hearing about here, not only is that an anomaly, but I'm going to call that a foo anomaly, because this corresponds to a kind of use case I know. This is the check that the credit card is working before you use it pattern. Yeah, and we haven't thought about that, but it's a great idea, obviously. Yes.
Can you say a little more about diversity? Because diversity will definitely change the efficacy of query versus anomaly. And so it seems
Right.
like a quick trick that can completely change your metric, or is that not true?
No, we would really have to also have something in our metric that rewards diversity. Like, well, as you say, if we could essentially present a group of proposed anomalies and say, we think these points are all anomalous for the same reason, are we right? And get feedback on the whole group at once, then that would be great. And then the next query we would use obviously a different group. But we might have to balance them. I know in real situations, I remember years ago I visited Bell Labs, and Daryl Prejabun was working on payphone fraud for it wasn't even AT&T at the time. And they had something kind of, some statistical model, and they were looking for weird behavior, but they also ranked them by how valuable they were, right, in terms of the financial impact of those frauds. So that was yeah. Okay, well, I better move along because we're really behind. So let's talk about these two applications. So the first one is data cleaning in weather networks. So I'm part of a group that's working on something called the Trans-Africa Hydrometeorological Observatory. And it's founded by two folks. One is a colleague of mine, John Selker, who's a hydrologist, and the other is a guy named Nick Van de Giesen, who's at the Technical University at Delft, and also a hydrologist. And they were at some World Meteorological Organization meeting at which this plot was put up showing where are there weather stations around the world that reliably report data to the World Meteorological Organization. And those blue dots are the ones that are the good weather stations. And we can see that in most of Latin America and Africa, the weather infrastructure is just very poor. And so they in the context of agriculture in Africa, most agriculture is rain-fed. There's not a lot of irrigation. And so, and they noted that when you have very poor sensing, then you can't buy crop insurance because the insurance companies don't know what risk they would take. They don't know how to price the insurance. And so that leads the farmers to plant their plants very far apart so that each plant, under the worst case precipitation conditions, will still get enough water to do well. And there have been field trials showing that if you do offer crop insurance, then the farmers plant much more aggressively, plant their plants much closer together, and get a much higher agricultural productivity as a result. So this is one of these examples of, if we could provide better data, this could lead to a crop insurance industry, which could in turn lead to higher agricultural productivity. So, John Selker is not a modest man. He wants to have Africa leapfrog over the whole rest of the world and become the best sensed continent. And of course, the price of sensors is dropping rapidly, and we can now build weather stations that are very cheap. And so we're trying to deploy 20,000 such stations across Africa and then create various data products. And I like to say, well, weather stations are really cool, but for some reason people want to put them out in the weather and expose them to the rain and all kinds of problems, and then they break. And so, this is a kind of Internet of Things project, and I like to say the Internet of Things is going to be the Internet of broken things. And so how can we automatically detect which stations have failed, which sensors have failed? And so we might approach this as a sort of medical diagnosis problem. If we could say, well, these sensors tend to get 1 of 5 different diseases. Can we learn to recognize the symptoms? But this is one of those cases where we feel like it seems to be an unbounded number of ways these weather systems can fail. Where there are known symptoms, we can write rules for them or build probabilistic models, but we want to use anomaly detection to detect new kinds of failures. I think in the interest of time, I won't go through all the technical stuff here, but I'll just say that we are combining anomaly detection scores in a dynamic Bayesian network where we reason about the state of each sensors, and then we're doing a form of map inference to try to say, given the observations that we've made turned into anomaly scores, we try to not just flag the data with anomaly flags, but actually do some root cause analysis and say the reason that you got this, 2,000 alarms is due to one particular thermometer failing for some time interval. So I guess I should say, maybe the most interesting or weirdest move here is, a typical problem you have when you try to model, do diagnosis on this is you want to model the sensor readings as a function of the state of the sensors. But these sensor distributions can be very messy. And so we replace the actual distribution of sensor readings by the anomaly score assigned to those sensor readings. And this has a nice virtue of normalizing everything to be in 0, 1 and having a more predictable distribution. At least that's our hypothesis. But we don't have definitive results to prove this. And so I'll say we're currently working a lot on comparing sensor readings at multiple stations. So then the other problem, which is more related to open world, is open category classification. So given that I have training data for, say, K classes that I've collected, and I train a multi-class classifier for them, but then my test data may contain queries corresponding to new classes, how can I detect them? Those we call them alien queries, the queries that belong to new kinds of objects. And so our approach is, given our training data, we train both our multi-class classifier, but also an anomaly detector. And so then when an input query comes in, we look at the anomaly score, and if it's greater than some threshold, then we reject that point and say, we think this might belong to a new category, so we're not going to classify it. But otherwise, we feed it through our classifier and make our prediction. And so this for me, was motivated by another ecological problem, which was for about a decade, I was working with some folks at the EPA and on campus at freshwater stream health monitoring. So the EPA every year in the United States does a sort of randomized sampling of freshwater streams. And what they do is they use a kick net, which is what these guys are doing here, to collect insect larvae that live on the substrate of the streams. And then they bring those specimens into the lab, and currently they manually identify them to genus or species. But this is very time consuming, and so we thought, well, we'll build a sort of robotic device that can singulate the specimens, as they say, and then photograph them, and then we'll use computer vision to tell them apart. And we did this back in the mid-2000s when everything was bag of SIFT and support vector machines as the classification technology. But we got up into the low 90% correct over, well, ultimately 54 categories. So we were all excited about that. And then we started to look at actually deploying it, and we realized, well, although our collaborators had collected specimens, and we had these beautiful training data for all the specimens, the test samples are going to contain other stuff. There's more than, it turns out, more than 29 species or more than 54 species out there. Like, it's estimated there's something like 1,200 species of freshwater macroinvertebrates, as they call them. So this led us to think about, well, how could we deal with this problem? And of course, more recently in computer vision, this has become a popular problem. So there are several techniques that are out there. But as far as we know, no one has looked at the question of whether we can provide any kind of theoretical guarantees. So we're looking at a setup now where we have two training sets. One training set is of our clean training data. You know, our collaborators went out and collected all these training data for us. It's all nicely labeled, and we know there are no contaminating samples in these. But in addition, we're going to require that we have a unlabeled collection of samples that are representative of our test queries. And so here we are making the well-defined anomaly distribution assumption that we can get a sample from the distribution of anomalies. In fact, to even talk about what it would mean to have a PAC guarantee on detecting, say, 99% of all of the aliens, right there, I'm assuming that that's a sensible statement, that there is such a distribution. And so we're going to assume that this contaminated sample, which we'll call SM for mixture, is a mixture where, again, the proportion of the aliens is alpha, and so this density is a mixture of 1 minus alpha times the clean distribution, P naught, times alpha times this anomaly distribution. Now, what we want to find is, let's suppose this is the CDF of the anomaly scores of the anomaly points. And so we're really interested in, say we want to detect 95% of the aliens, or anomalies, then we want to know this quantile, right? The anomaly score such that 95% of the probability mass is greater than that. So we'd like to estimate this tau at 0.05 or 0.01 or whatever we want. So we'll call this Q quantile 0.05. So we note that if this is a mixture distribution, since we're in one-dimensional world, it's true that for the cumulative distribution functions also, that the CDF of the anomaly scores for the mixture distribution is a convex combination of the nominal distribution and the anomaly distribution. So if you do a little algebra, you can say, well, gee, the anomaly CDF can be calculated. We can estimate this from data. We can estimate this from data. And if someone will just tell us alpha, then or give us maybe a reasonable upper bound on alpha, then we can use that to estimate this CDF. And so the picture looks something like this. This might be the CDF of the clean data. The black one is the mixture data, and maybe this is our anomaly CDF. And so we're going to set our threshold somewhere around in here, maybe, right? And we'll get all of the anomalies, but we will have some number of false alarms, too. So, of course, this all depends on how good the anomaly detector is and how well it can distinguish the aliens from the known classes. So when we look in practice, this is our empirical CDF of the of the clean data. This is the empirical CDF of the mixture data, and of course we're kind of subtracting them. And so unfortunately, this thing can go negative. This is the estimated CDF of the anomalies. So it's pretty sad. But if we have a larger sample, it starts to look reasonable. And, but it still can cross this threshold a few times. And so we look at the largest value of the anomaly score that crosses this 0.05 line, and we set our threshold there. And that's what this pseudocode says. And then we're able to get a guarantee that if the number of samples in these two data sets is equal to n, then the required sample size is something like this. We have a 1 over epsilon squared term. We have something that's sort of a 1 over alpha squared term. And then we have this, which is a funny thing that comes from the fact that we're estimating two different cumulative distribution functions, and there are some concentration results for CDFs. And so then with probability 1 minus delta, the alien detection rate will be at least 1 minus q plus epsilon. So once again, we need some elbow room in the form of some epsilon. And so anyway, so that's what we can do. And then experimentally, I didn't put the results here, but we have a paper under review for ICML where we also show experimental results for this. And of course, it's a loose bound, but it is a bound, and it does work in practice. And we see that for some reasonable things, so we have some results on some image data sets and some benchmark data sets. We get false alarm rates using isolation forest as our anomaly detector. False alarm rates somewhere in the 10 to 20% range for reasonable sample sizes. So So we're very happy with this, very pleased with it. So to finish then, outlier detection, I talked about the different unsupervised and mixed. Our benchmarking suggests that this isolation forest algorithm is quite nice. And surprisingly that these percentile methods or quantile methods are not doing so well. I should say in passing, obviously these things don't work at all well by themselves for image data. We've kind of discussed this already. Any kind of signal data or time series data. And so I think the next steps here are I'm very intrigued by things like GANs and autoencoders and other kind of manifold learning and density estimation techniques that are coming out of the deep learning literature. And so that's the next thing I want to try is there's some very nice papers at the last couple of NIPSs about this, and because I think that might give us much better anomaly detectors than we can get using these simple IID feature-based methods. Then we talked about the RPAD theory, which accounts for their behavior, I think, reasonably well. Then we talked about simple presenting the most important features, a simple ordered feature explanation, incorporating expert feedback using this accuracy at the top strategy, and finally, guarantees for open category detection. I apologize for running long, and thank my funders and open it up for questions. Thank you very much. Yeah.
So, at the beginning of the talk, you mentioned that there was a fundamental assumption about the nominal distribution and the anomaly distribution.
Well, the assumption I wanted to call out is it safe in my application to assume that the anomalies come from a well-defined distribution?
Right. And I'm curious, can you sketch how to weaken such an assumption to allow the fraudster also in the loop, not just the analyst in the loop, but an arms race between the anomaly detector and the people who are trying to game the thing?
Well, so I don't know how to do that in a theoretical framework. It seems to me that we end up in having to think about it more like a game or a mini-maxing kind of adversarial learning setup instead to get it and try to get some guarantees that way. So that would be quite different from this. And of course, there is some interesting work in supervised learning, adversarial learning for supervised learning. And of course, everybody in deep nets right now is trying to deal with adversarial examples in deep learning. And obviously, some of the strategies that are being explored, like using GANs and trying to map queries onto the data manifold to strip out these adversarial attacks, that many are very closely related to these same ideas of could we detect the adversarial queries as being outliers that fall outside of our data distribution. I think anomaly detection will again be part of the answer, but this theory for open category will not be part of the answer there. We need some other more adversarial approach.
And just a clarification, was the DARPA Adams thing run as an arms race between red and blue team, or was it?
So there was a red team that was actually based on people from CERT, the computer security guys, and they have this whole white paper on different kinds of insider threats in organizations that they've collected both from DoD and from industry. My favorite one is what they call the insider startup, that a sub-team decides, the company doesn't appreciate us, we're going to take the source tree with us and go form a startup. But there were other things like, there were things like, someone who was passed over for promotion, survivor guilt, all these. And so they have this whole set of things, a lot of them very psychological. And then they hired a scriptwriter to kind of write scripts about what kinds of emails and text messages would these people be exchanging in addition to their desktop data. Then they acted out all of this under this desktop monitoring software and then overlaid it on the behavior of real employees in the company. And then we had to, had access to this in a very controlled setting, and we had to see if we could find those red team inserts. But unfortunately, we don't really know how hard they were. Yeah, and of course we don't have access to the data anymore. It would have been interesting to, once we had the ground truth labels, to go in and see, well, so how could we train a supervised learner, like could a nearest neighbor classifier figure this out quickly? We don't know, yeah.
In the weather station example, I'm curious. When most of the anomaly detection algorithms you talked about seem to be optimizing for really low false alarm rates and
Right.
high catches. But in some of the systems, depending on how you're reacting to the anomaly, you might be able to tolerate lots of false alarms, right? Depending on what's important and how you're recovering from a problem. I was kind of curious, in the weather station, what happens when you detect an anomaly?
Well, so in all existing weather networks that I'm aware of, they have a lot of flags, and then they rely on some human eyeballs to look at them all. So, for instance, Oklahoma Mesonet is the best weather network in the United States. They have a big budget, and they have 4 full-time meteorologists for 130 stations. So scaling that up to 20,000 stations in Africa, I need a heck of a lot of. I just don't think that strategy scales to the Internet of Things. So that's why I think we need to bring much more intelligence to bear. Also, most of the existing weather networks, they use basically hand-coded expert systems for writing these, problem detection rules, and so they're completely ad hoc. And so I think if we, I think in some sense low-hanging fruit for us, because by bringing probabilistic inference on top of the alarming, we should be able to greatly. We'll still have lots of alarms, but we can say this, these 1,000 alarms are really just due to one failure, and create a trouble ticket for it. So we're trying to build we are well on the way to building a system where there's sort of the weather network manager who every day logs in and he gets a report of what are the new failures we found since in the last 24 hours, and then he can very easily create trouble tickets and assign those to the field engineers who then will be scheduled to go out and do the repairs. And in our dreams, that would be integrated with an inventory system, and on and on. But that's how they're set up.
But you have a lot more knowledge than usually about how sensors failure. You can use sensor error models and
Right.
make it much richer. This reminds me of this national mission control era where experts had very rich models about how sensors fail. They would have just viewed it as doing weird things, but they failed certain ways.
Right. So I think, a real
than being sort of no priors on it.
A mature system, presumably, ultimately, we find these recurring anomalies, and so then they bring them into the lab and say, okay, what's going on here? And then, we've already had this happen. It wasn't due to we didn't discover with our code, but there was a manufacturing defect or a design defect in the station, and so all the Generation 2 stations are having to be replaced with. But right, over time you would accumulate a library of failure models, and with very specialized detectors for those. But we want this anomaly infrastructure as a fallback, because there's always something new. We haven't had any of our stations attacked by an elephant yet, but I'm sure it'll happen, right? And Oklahoma, they have unbelievable stories about cows getting into the thing, and it's just what is the symptom of a weather station where some ants have decided to lay eggs all over the circuit board? It's hard to have a disease model for that.
How you had a question?
Yeah, I was just wondering about the online case of anomaly detection. You seem to assume here in the problem statement that the nominal distribution is stable over time.
Absolutely, yes.
What happens if the nominal distribution starts drifting over time because system identification changes or whatever other issue?
Right, and so, somehow we're going to have to track that distribution. We haven't confronted that case here, although in the weather data case, it's not stationary, but it is very predictable on an annual cycle and a daily cycle. There are lots of periodic components that you can, with sort of traditional time series techniques, model and pull them out of the signal. And then, in your dream, you have now uncorrelated white noise, and then it looks. Maybe it's a part of the answer, but we've spent a whole year trying to do good feature engineering and decided this isn't working for us. So because it's just too much work to do all that modeling. And when you make modeling errors, then that introduces artifacts, and then we start making mistakes because of those. So we're looking now at basically looking at nearby weather stations that should be experiencing the same disturbances, the same annual and daily cycles, and then looking at, comparing them. How well can we predict one using the other, or what's their joint distribution, and using that to do the anomaly detection stuff. So, yeah, that's, I mean...
Some drift between the predictions?
Yeah, yes, and actually we need to retrain the models really on sort of a sliding window thing, because again, the nature of the correlations changes in wintertime. For instance, precipitation is it's our most important variable, our most problematic sensor, and it has the smallest spatial scale in terms of spatial smoothness. In the wintertime, right, if we think about the Pacific Northwest, it's a very, very smooth, very large storm, right? It affects the whole Pacific Northwest, and so if it's raining one place, it should be raining at another station, and we can use that correlation. But in the summertime or in the late spring, when we get these showers, stations become extremely uncorrelated, and so then we need to have, in a sense, switch models to use a model that corresponds to a showery day with lots of little cells. And really, I think we need to be tracking that, because it really is happening day by day, whether, like the first day of a rain event, it might have this large scale, and then by the third day, it's into these little uncorrelated things. And so, so I think we actually need to track that kind of larger spatial phenomenon. And speaking of larger spatial phenomena, another thing is if you have a spatially clustered set of alarms all ringing at once, it's probably a real weather event, an unusual weather event, not any of the stations broken. And that's, knowledge that it's not anywhere in our system, but the meteorologists definitely know this. And of course, there are other data sources like satellites and radar and things that we can use as additional sources of data for this. So,
okay, well, with that, we probably should thanks very much.
Thank you.